Tonight, a molecular signal has been linked to the James Webb Space Telescope, to the pillar-like walls of the Boomerang Nebula, and to a form of motion astronomers supposedly cannot explain. The signal may be real. The attribution and the word vibration are where the trouble begins. The Boomerang Nebula unquestionably contains molecules behaving under extraordinary conditions. Parts of its outflow became colder than the microwave background of the universe. Carbon monoxide lines reveal gas travelling at different speeds through a layered structure hidden beyond the famous blue lobes. Hubble and ALMA have both exposed pieces of that structure. But before we call this a Webb discovery, 3 questions have to be separated. Which telescope recorded the feature? Which molecular transition produced it? And does the pattern show a true oscillation, or several regions of gas moving, absorbing and emitting at different velocities? Those questions are not technical escape routes. They are the mystery. A molecule can rotate between quantized energy states. Its bonds can stretch or bend in vibrational modes. The cloud carrying that molecule can move toward or away from Earth, shifting the observed frequency. Cold foreground gas can absorb radiation from warmer material behind it. Several normal components can overlap and create a line that looks anything but normal. One waveform can hide several physical stories. By the end of tonight, you're going to understand what astronomers actually mean when they describe molecular rotation and vibration, how the Boomerang Nebula became colder than the cosmic background surrounding it, what Hubble and ALMA truly revealed, what Webb could test in the infrared, and what evidence would be required before this signal could honestly be called unexplained. Before we get started, if you love exploring the depths of space, like the video or subscribe for more quiet journeys through the science hidden inside the universe's strangest objects. Now, let's begin. The first confirmed anomaly did not come from Webb. It came from radiation that failed to reach us. Behind the Boomerang Nebula lies the faint microwave afterglow of the early universe. It fills the sky at roughly 2.7 Kelvin. At frequencies associated with carbon monoxide, part of that ancient background disappears when it passes through the nebula. The molecules absorb it. Astronomers detect a narrow absence where slightly more radiation should have arrived. That missing light is the first hard fact in this investigation. It proves that molecular gas lies in front of the cosmic background. Its depth and spectral shape reveal how the carbon monoxide energy levels are populated. Combined with physical modelling, it shows that parts of the foreground outflow became colder than the radiation behind them. The nebula is not merely cold. It is cold enough to cast a molecular shadow against the afterglow of the Big Bang. That finding existed before the current Webb claim. Later observations added visible structure, molecular velocity and dust. Together, they created the evidence base against which any new infrared feature must be tested. The correct opening question is therefore not whether the boomerang contains strange molecular physics. It does. The question is whether the alleged signal belongs to Webb, whether vibration is the right description, and whether known physics can account for the pattern before something genuinely new is invoked. The Boomerang Nebula is not the remains of an ordinary explosion. It is a star caught between 2 forms of death. The system lies roughly 5,000 light-years away in the southern constellation Centaurus. At that distance, the light reaching Earth tonight began its journey long before telescopes existed. Long before modern astronomy had names for dying stars, and long before anyone understood that the soft blue shape in this part of the sky was recording one of the shortest and most unstable phases in stellar evolution. Astronomers usually describe the boomerang as a preplanetary nebula, also called a protoplanetary nebula. The name is unfortunate. There are no planets being created here. The word planetary survives because early astronomers looking through small telescopes thought some round nebulae resembled the disks of distant planets. The objects were unrelated, but the name remained. A planetary nebula is actually created near the end of a star's life. For most of its existence, a star similar to the Sun maintains a delicate balance. Gravity pulls matter inward. Energy released in the core pushes outward. The balance can persist for billions of years. Eventually, however, the usable hydrogen in the core becomes depleted. The star's internal structure changes, the outer layers expand, and the star becomes a red giant. Later, during a phase known as the asymptotic giant branch, the star can swell enormously, pulsate and lose material through a dense stellar wind. The star begins giving itself away. Atoms, molecules and dust flow outward into space. Over time, the exposed stellar core becomes hotter while the expanding envelope moves farther away. If the core becomes hot enough, its ultraviolet radiation begins tearing electrons from atoms in the surrounding gas. The gas then glows with the bright colours associated with a mature planetary nebula. The Boomerang has not fully reached that stage. Its central star has already expelled an extraordinary amount of material, but the core is not yet illuminating the entire surrounding cloud as a mature planetary nebula would. Much of the light we see is instead starlight scattered by dust inside the lobes. That places the Boomerang inside a remarkably narrow interval. The star has left the most violent part of its giant phase, but the expanding envelope has not yet become a fully ionized planetary nebula. In astronomical terms, this transition is brief. It may last only a few thousand years, perhaps less depending on the star's mass and the rate at which its exposed core heats. That sounds long only because we are human. Compared with a stellar lifetime measured in billions of years, the preplanetary phase is a heartbeat. Imagine compressing the complete life of a sun-like star into a single human day. The star would spend almost the entire day burning steadily. The giant phases would arrive late in the evening. The state we see in the Boomerang might occupy only the final seconds before midnight. And somehow, we are observing it during those seconds. The familiar blue structure makes the object appear calm. Two broad lobes extend away from a dark centre, forming something that resembles a bow tie, an hourglass, or the curved arms of a boomerang. Fine arcs and faint filamentary structures sit inside the brighter regions. From a distance, the whole object looks almost symmetrical. But symmetry in an image does not mean gentleness in the event that produced it. The material surrounding the central star was not placed there slowly and evenly. It was expelled during periods of intense mass loss. Different regions were launched at different times, in different directions, and perhaps through different physical mechanisms. The dark central band is especially important. Somewhere behind that dense waste lies the source of the entire structure, the aging stellar core and whatever remains of the system that surrounded it. Dust blocks much of the direct visible light. Radiation escapes more easily in the polar directions, illuminating material above and below the waste. That escaping light helps create the famous bipolar appearance. But the bright lobes are not simply two solid objects attached to the star. They are cavities and walls inside a much larger envelope. Some regions become visible because light reaches them and scatters toward Earth. Other regions remain dark even though matter is still present. The star is not sitting inside an empty bow tie. It is buried within a vast layered outflow. This already creates a problem for any claim about something happening inside the pillars. The features that look like pillars or sharply bounded walls may be places where density, dust and illumination combine to produce contrast. They are real structures, but what we see depends heavily on the wavelength used to observe them. Visible light reveals where photons escape. Radio observations reveal cold molecules. Infrared light can reveal warmer dust, molecular excitation and material hidden behind regions that visible light cannot penetrate. The object changes as the instrument changes because each instrument responds to a different physical component. The Boomerang is therefore not one picture waiting to be viewed more clearly. It is several overlapping physical systems, scattered light, cold molecular gas, dense dust, expanding cavities, high-speed material, and a concealed stellar center. And all of them are evolving. The outermost matter left the star long before the material closer to the center. As the gas travels outward, it expands into a larger volume. Its density falls. Its temperature changes. Radiation from the star interacts with it differently. Collisions between molecules become less frequent. Some regions remain shielded. Others begin to warm again. The shape we observe is a record of time. Distance from the central star becomes a rough history of mass loss. Older material generally lies farther away. Younger structures remain nearer the center. Changes in velocity, density and direction preserve evidence of changes in the star or in the system surrounding it. But reading that record is difficult. A telescope does not show the event unfolding from the side. It receives light and radiation projected onto a flat sky. Material from the front, center and rear of the nebula can overlap along the same line of sight. A bright feature might be dense, strongly illuminated, or simply positioned at an angle that sends more scattered light toward us. Astronomers must reconstruct the three-dimensional object from incomplete clues. The boomerang's apparent symmetry also hides a more unsettling possibility. A single isolated star may not be able to produce everything we observe. Ordinary stellar winds can remove enormous amounts of material, but the boomerang's outflow is unusually massive, unusually fast and unusually energetic. Its dense waste and strongly bipolar inner structure suggest that something redirected or intensified the mass loss. A second star may have been involved. We will come to that companion later, because the evidence does not show us a neat image of two stars colliding. It gives us the aftermath, expelled mass, velocity patterns, a buried center, and an energy budget that is difficult to explain through a quiet, solitary death. For now, the important point is simpler. The Boomerang Nebula is young, but the star that created it is ancient. It is beautiful, but the beauty is produced by violent mass loss. It looks like a single blue structure, but most of its matter extends beyond the visible lobes, and it appears almost frozen in place even though its gas is racing outward. The object is balanced between opposites. Old star, young nebula, violent expansion, extreme cold. Hidden center, illuminated walls. A structure thousands of years in the making, observed during a transition that will soon erase the very conditions that made it famous. Because as the central core continues to evolve, it will grow hotter. Its radiation will eventually transform the surrounding gas. The ultra-cold state will not last. The scattered light nebula will change. The molecular material will disperse, warm, or become ionized. The boomerang is not a permanent monument. It is a temporary physical event. And the most extraordinary evidence of that event did not come from its bright blue lobes. It came from carbon monoxide in the darkness beyond them, from gas so cold that the universe behind it appeared warmer. To understand how astronomers discovered that cold, we have to look not at the light the nebula produced, but at the ancient light it removed. The ancient light behind the Boomerang Nebula began travelling toward us almost 14 billion years ago. It is the afterglow of the early universe, stretched by cosmic expansion into microwave radiation and cooled to a temperature of about 2.7 Kelvin. It fills every direction in the sky, even where space appears completely black. That faint radiation is still there. The Boomerang Nebula sits in front of part of it, and in a narrow range of frequencies associated with carbon monoxide, the nebula absorbs some of that background glow. That is how its deepest cold became visible. Not through brightness, through absence. To understand why, imagine placing a thin cloud in front of a softly glowing wall. If the cloud is warmer than the wall, it may add its own light. If it is colder and contains material able to absorb the wall's radiation, it creates a darker patch. The carbon monoxide in the boomerang performed the second role. Microwave radiation from the cosmic background entered the cloud from behind. At precise frequencies, carbon monoxide molecules absorbed part of that radiation. Radio telescopes detected less energy coming from the direction of the nebula than they expected from the background alone. The cloud appeared in absorption. And for that to happen so strongly, parts of the molecular gas had to possess an excitation temperature lower than the microwave background behind them. That phrase, excitation temperature, needs care. It does not mean that every molecule in the cloud has exactly the same speed or energy. It describes how populations of molecules are distributed between particular energy levels. Astronomers use those populations to understand how the molecules interact with radiation. Carbon monoxide is especially valuable because it has a simple, strong pattern of rotational transitions. The molecule consists of one carbon atom and one oxygen atom bound together. It can rotate only with specific allowed amounts of energy. When it changes from one rotational state to another, it absorbs or releases radiation at a precise frequency. Those frequencies act like identification markers. If a telescope detects one of the expected lines, astronomers can recognize carbon monoxide. If the line is shifted, the gas is moving. If it is broadened, several velocities may be present. If it appears in absorption, the foreground molecules are removing radiation from a brighter background. A single line can carry several kinds of information at once. That is useful. It is also dangerous if the language becomes careless. A line changing shape does not automatically mean that the molecule itself is displaying a new kind of vibration. It may mean that one region of gas is approaching while another recedes. It may mean that colder material sits in front of warmer material. It may mean that the line has become optically thick, so radiation cannot pass freely through the cloud. It may mean that several physical layers overlap from our point of view. The boomerang contains all the ingredients needed to create complicated spectra without requiring unknown molecular physics. It has a hidden central source. It has cold outer gas. It has warmer inner regions. It has dust. It has dense walls. It has material moving toward us and away from us at different speeds. And because we observe the entire structure from thousands of light years away, those layers are compressed into the same line of sight. A spectrum separates some of that confusion. The frequency tells us which transition we are observing. The amount of shift from the expected frequency reveals velocity along our line of sight. The intensity gives information about temperature, density and molecular abundance, although those quantities are often entangled. The width and shape of the line reveal whether one smooth flow or several separate components contribute to the signal. But a spectrum is never just a voice recording from a molecule. It is the final result of molecules, radiation, motion, geometry, and the telescope itself interacting. This is why the boomerang's cold required more than seeing a dark line and declaring a temperature. Astronomers had to model how carbon monoxide should absorb the cosmic microwave background under different conditions. They had to estimate how much gas lay along the line of sight. They had to consider the population of rotational energy levels. They had to account for expansion and for emission from other regions of the nebula. The conclusion was not that the whole object sits uniformly at one simple temperature. The conclusion was that parts of the expanding molecular outflow had become extraordinarily cold, colder than the 2.7 Kelvin background radiation surrounding them. In some descriptions, the temperature is given as roughly 1 Kelvin. That number is so small that it can create the wrong image. At 1 Kelvin, molecules do not freeze into complete stillness. Absolute zero would represent the lowest possible thermal limit, and even the concept of perfect stillness becomes complicated in quantum physics. The boomerang is above that limit. Its molecules retain motion. They collide. They rotate between energy states, and the entire cloud is expanding at tremendous speed. the gas can be cold and violent at the same time. Thermal motion describes the random microscopic movement of particles relative to one another. Bulk motion describes the cloud as a whole moving outward from the star. These are different scales. A crowd of people can move rapidly down a street while remaining quiet and orderly relative to one another. The boomerang's molecular gas is similar in one narrow sense. The outflow races through space, yet the random internal motions associated with temperature can remain extremely small. This distinction is essential to the title's supposed vibration. If two sections of the nebula move at different speeds, their spectral lines appear at different frequencies. The result may resemble multiple peaks or a wavering pattern, but the pattern is not necessarily showing molecules physically oscillating together. It may be showing different layers of an expanding flow. The boomerang's velocity structure is not a minor detail. It is one of the reasons astronomers needed ALMA. Earlier observations could establish that the object contained exceptionally cold molecular gas. ALMA could resolve far more of that gas spatially and divide it into velocity channels. Instead of receiving one blended spectrum from a large region, astronomers could examine how the carbon monoxide signal changed across the nebula and across different speeds. The cold was no longer only a number. It became a map. That map would later reveal that the visible bow tie sits inside a much larger molecular structure. It would show dense walls corresponding to the illuminated lobes. It would expose material extending far beyond the regions Hubble made famous. But before that map could be interpreted, astronomers had to explain something even more basic. How did gas expelled from a dying star become colder than the natural microwave background of space? Space itself did not refrigerate the cloud. The boomerang's expansion did. As gas moves outward into a larger volume, it can perform work on its surroundings. Energy that once contributed to internal motion is converted into expansion. Collisions become less energetic. The temperature falls. This is adiabatic cooling, and it is familiar on Earth. Gas escaping from a pressurized container can become cold. Air rising through the atmosphere expands as pressure decreases and cools. The boomerang follows the same broad thermodynamic principle, but on a scale large enough to surround a dying star. The expansion had to be extraordinarily rapid. A slow wind would not have produced the same degree of cooling before other sources of energy began warming the gas. The envelope was expelled so forcefully that it expanded faster than radiation, and collisions could restore the lost heat. The nebula became a cosmic refrigeration event. But that phrase can still sound too gentle. Nothing about the origin of this cold was gentle. The material had to be torn away from the central system, accelerated outward and spread through an immense volume. The cold is the thermal scar left by violent mass loss. And this creates the next problem. An ordinary aging star can lose its atmosphere. It can produce a stellar wind. It can form dust and surround itself with an expanding envelope. The boomerang appears to have done far more. Its molecular outflow is not only cold, it is enormous, massive and fast. The same expansion that created the low temperature also demands an energy source powerful enough to launch the gas in the first place. So the cold measurement does not close the mystery. It opens a deeper one. The universe behind the nebula tells us that the gas lost an extraordinary amount of internal energy. The velocity of the gas tells us that an extraordinary amount of energy was used to throw it outward. Somewhere inside the hidden center, those two facts must connect. And when astronomers followed that connection, a quiet single star was no longer enough. The Boomerang Nebula had lost too much mass, pushed that mass too quickly and cooled it too efficiently for the simplest explanation to remain comfortable. At first, the cooling mechanism appears straightforward. Gas leaves the star, the pressure around it falls, the cloud expands into a larger volume. To keep expanding, the gas performs work, and that work draws energy from its internal motion. The temperature drops. This is the same broad reason air cools as it rises through Earth's atmosphere. It is also why gas escaping from a pressurized container can feel cold against your hand. The gas spreads out. Its molecules collide less energetically. Energy that once appeared as heat becomes part of the work required to occupy more space. The boomerang followed that principle on a stellar scale. But scale changes everything. The escaping gas was not expanding across a room or rising through a few kilometers of atmosphere. It was traveling outward from a dying star, crossing distances measured in thousands of astronomical units, and eventually occupying a region extending far beyond the bright lobes visible in ordinary images. 1 astronomical unit is the average distance between Earth and the Sun. The ultra-cold outflow of the boomerang extends across more than 100,000 of those units. Place the Sun at the center, move beyond Earth, beyond Jupiter, beyond Neptune, and far beyond the familiar planets. Continue through the distant reservoir where comets may orbit. Keep going. The molecular material associated with the boomerang's great cold outflow would still be spreading around you. The object presented in the famous blue image is only the illuminated inner portion of something much larger. That vast expansion helps explain the temperature. The gas was diluted so quickly that it cooled below the microwave background before surrounding radiation could restore its heat. Yet the same observation creates an immediate contradiction. Cooling requires the gas to expand. Extreme cooling requires it to expand very rapidly. And rapid expansion requires energy. A remarkable amount of it. Parts of the boomerang's molecular outflow move at speeds approaching roughly 164 kilometers per second. That is not the random thermal motion of one molecule. It is the outward movement of the cloud itself. In a single second, material traveling at that speed could cross the distance between many neighboring cities. In 1 minute, it would move almost 10,000 kilometers. Given enough time, the gas can spread across a region large enough to make the bright inner lobes look almost small. This is the central inversion. The boomerang became extraordinarily cold because it experienced an extraordinarily violent expansion. The quietest thermal environment emerged from one of the most energetic mass loss events known around a star of this kind. Cold on the microscopic scale. Violence on the astronomical scale. They are not opposites here. They are cause and consequence. A normal wind from an aging star can also cool as it expands. Red giants routinely lose material. Their outer layers become weakly bound. Pulsations lift gas away from the surface, and radiation pressure acting on dust helps push the material into space. But the boomerang's outflow appears excessive even by those standards. The mass involved is too large. The speed is too high. The kinetic energy, the energy of motion, is too great. A solitary star can release a great deal of material during the final stages of its life, but there are limits to how efficiently its radiation and pulsations can accelerate that material. When astronomers compare those available energy sources with the observed outflow, the numbers begin pulling apart. The gas seems to demand more than the star should have been able to provide by itself. This does not instantly prove that another star was present. Astronomy rarely offers conclusions that cleanly. We do not possess a recording of the event from the moment it began. We see the expanding aftermath. We measure the gas. We estimate its mass. We map its velocity. We reconstruct the timing. Then we ask what physical event could have left those measurements behind. The boomerang preserves several distinct episodes. The oldest material lies farthest from the center. It was expelled first and has had the longest time to travel. Younger material remains closer to the star. Dense structures near the central waist and the sharper bipolar cavities appear to belong to later stages of the event. The geometry didn't remain constant. The rate of mass loss changed. The direction of the outflow changed. the speed changed. Something transformed a broad envelope into a more strongly shaped bipolar system. That transformation is important because a spherically expanding wind is relatively easy for a solitary star to produce. A dense equatorial waste combined with fast polar flows usually requires another mechanism to organize the gas. Rotation can contribute. Magnetic fields may contribute. But in many preplanetary nebulae, the most powerful sculptor is a companion star. A companion can orbit inside or near the expanded atmosphere of a giant. It can disturb the envelope. It can concentrate material toward the equatorial plane. It can redirect gas toward the poles. And if the interaction becomes close enough, the companion may enter the giant star's outer layers. At that point, orbital energy becomes available. The two objects spiral closer together. As they do, energy and angular momentum are transferred into the surrounding envelope. Gas that was only loosely bound to the giant can be accelerated and expelled. The orbit shrinks. The envelope expands. An enormous reservoir of gravitational energy is converted into motion. This is one of the leading routes toward explaining outflows that ordinary stellar winds cannot power. But we're not ready to place that companion at the center of the story yet. First, we need to understand how the gas itself records the expansion. The outflow is not one smooth shell moving at one speed. Different regions produce different spectral signatures. Gas on the near side moves partly toward Earth. Gas on the far side moves partly away. Material traveling across our line of sight contributes different velocity components. Dense regions absorb radiation differently from thin ones. When all of those components enter the same telescope beam, the resulting line can broaden, divide, or develop complex shapes. This is where supposed molecular vibration can begin to emerge from ordinary motion. Imagine listening to several trains passing a station from different directions. Each horn may produce the same original note, but the motion of each train shifts the frequency reaching you. Combine them, and the recording becomes complicated. The sound has not discovered a new law of acoustics. Several moving sources have overlapped. A molecular spectrum from an expanding nebula can behave in a comparable way. The molecule's known transition provides the reference frequency. Motion shifts that line. Geometry determines which parts overlap. Temperature and density determine whether each region emits or absorbs. The apparent anomaly may be an encoded map of the outflow. To decode it, however, astronomers need more than one blended spectrum. They need spatial resolution. They need to separate the signal coming from the central waste, the cavity walls, the outer cloud, and the approaching and receding sides. That is what ALMA made possible. Its observations transformed the boomerang from a cold source with a peculiar line profile into a molecular structure divided by position and velocity. The telescope array could identify where particular speeds appeared across the nebula and how those regions related to the blue lobes seen by Hubble. And that comparison exposed something the visible image had concealed. The bright bow tie was not the full extent of the outflow. It was the lit interior of a much larger event. The gas responsible for the extreme cooling continued far beyond the edges that appeared to define the nebula. Material existed where visible light showed almost nothing. The dark regions were not empty. They were simply hidden from that particular kind of observation. So the next question is no longer how a small blue bow tie became cold. It is how an enormous molecular cloud came to look like a narrow pair of glowing lobes. The answer lies in dust, illumination and walls that appear solid only because light has selected them from the darkness. In the famous Hubble images, the Boomerang Nebula seems to be built around two opposing blue structures. They rise above and below a narrow central waist, widening outward like the halves of an hourglass. Inside them, faint arcs and filaments appear stacked one behind another. Some are narrow enough to resemble pillars, ribs or frozen waves. The image feels architectural. It looks as though the dying star constructed two enormous chambers and left bright walls standing inside them. But a nebula is not a building, and visible light does not provide a simple map of where all its material is located. Hubble records photons that reach its mirror. In the Boomerang Nebula, many of those photons began near the hidden central star, escaped through less obstructed directions and then scattered from dust grains toward Earth. That means brightness depends on more than density. A region can appear bright because it contains more material. It can also appear bright because the angle of scattering directs more light toward us. Another region may contain just as much gas and dust, but remain nearly invisible because it receives less illumination or sends the scattered light somewhere else. Light chooses what the image reveals. Near the center of the boomerang, a thick concentration of dust blocks the star along the equatorial direction. We see this region as the dark waste separating the two lobes. Radiation escapes more easily through the polar openings above and below it. Those openings function like broad cones. Starlight enters the cavities, strikes their inner surfaces and illuminates the dust along the walls. From Earth, the selected surfaces appear sharply defined against the surrounding darkness. This is where the title's pillars must be handled carefully. The word works as an immediate visual description. It gives the listener something solid to imagine. Yet the relevant physical structures are more accurately described as cavity walls, dense molecular boundaries, arcs, filaments, and sections of a bipolar outflow. They are not stone columns suspended in space. They are shaped regions of gas and dust. And even those regions may not be as sharply separated from their surroundings as the image suggests. A gradual change in density can look like a hard edge when illumination changes suddenly. A curved wall can appear like a narrow line when we see it nearly from the side. Separate layers can overlap in projection and create the illusion of one continuous structure. The image is real. The interpretation requires geometry. Imagine a thin, curved sheet of smoke in a dark room. Shine a lamp across it from one side. Most of the sheet remains faint, but one edge catches the light and becomes a bright line. From a distance, that line may look like a solid rod. Turn the lamp slightly, and the rod disappears. The smoke has not moved very far. The illumination has. Something similar can happen across a nebular cavity. The bright feature is not false, but its apparent solidity may come from the relationship between the material, the hidden star, and the observer. Hubble revealed that the boomerang's lobes were much more complicated than the earlier ground-based images suggested. The smooth outer shape contained arcs, loops, and fine filamentary structures. These details preserved evidence of uneven mass loss and changing conditions near the star. Some arcs may mark episodes when more material was expelled. Others may trace instabilities where faster gas interacted with slower gas. Curved surfaces may belong to shells launched at different times. Small variations in density can become visible when starlight passes through them. The nebula did not grow as one perfectly smooth wind. It accumulated history. Every layer had a different starting time. Every parcel of gas carried a direction and speed. Dust formed, moved outward, and changed the way later radiation travelled through the cloud. So the visible walls are not merely decoration surrounding the central mystery. They influence the spectrum. A molecular line measured through a bright cavity wall may contain contributions from several locations. Cold foreground gas can absorb radiation from warmer material behind it. Gas on the near side of the expanding structure may move toward Earth. Gas on the far side may move away. A dense filament may contribute a stronger signal than the more diffuse material around it. If those components overlap, the resulting line can divide into peaks, develop an asymmetric shape or change intensity from one position to another. To an untrained eye, the changing pattern may look like a wave passing through the structure. but the spectrum may not be recording a wave at all. It may be separating geometry. This is one reason a single image cannot confirm a molecular vibration. The image identifies apparent structures. Spectroscopy identifies energy transitions and motion. To understand what is happening, astronomers must align the two. Does the unusual line appear only along one illuminated wall? Does it follow the velocity of the expanding gas? Does the same feature appear on the opposite side of the nebula? Is it associated with colder material, warmer material, or a region where the two overlap? Does its frequency match a known molecule? And most importantly, does it remain fixed in space, or does it change with time? Without those answers, the word vibration can hide more than it reveals. The boomerang is especially vulnerable to this confusion because its famous optical appearance is so persuasive. The blue lobes look like the complete object. The dark boundary around them looks like empty space. But cold molecular observation showed that matter continues far beyond those visible edges. The bright cavities exist inside a much larger outflow. The darkness surrounding the bow tie is not necessarily empty. Much of it simply does not scatter enough visible light toward Earth to dominate a Hubble image. This is the inversion that changes how the nebula must be imagined. The central star expelled an enormous cloud. Within that cloud, later processes carved, compressed, or illuminated opposing cavities. Hubble showed the lit architecture inside the event. It did not show the full event. Once that becomes clear, the apparent pillars take on a different role. They are not isolated objects waiting to vibrate. They are sections of a dynamic boundary between regions with different density, temperature, illumination, and motion. A signal changing across those walls could be produced by ordinary but complicated physics. One side may be more strongly illuminated by the central source. One layer may contain more dust. A shock may compress gas locally. The near and far surfaces may overlap from our viewing angle. A molecule may appear in emission in one region and absorption in another. None of these possibilities requires a mysterious coherent oscillation, yet separating them demands an instrument capable of doing something Hubble was not designed to do. Hubble could show the scattered light in remarkable detail. It could reveal the arcs, filaments, and apparent walls, but it could not map the cold carbon monoxide outflow with the same direct sensitivity as a millimeter observatory. For that, astronomers turned to ALMA. High in the dry Atacama Desert, dozens of antennas could work together as one enormous observing system. Instead of looking for visible light reflected by dust, ALMA could detect radiation associated with cold molecules. It could divide a carbon monoxide line into narrow frequency channels and connect each channel with a different range of gas velocities. Suddenly, the nebula was no longer only a blue shape on the sky. It became a moving structure. Gas approaching Earth separated from gas moving away. Dense molecular walls emerged around the visible cavities. The great outer outflow appeared beyond the limits of the Hubble lobes. And the features that looked like pillars could finally be tested against the motion hidden inside them. A photograph had given astronomers the architecture. A spectrum was about to turn that architecture into a map. ALMA does not look like a conventional telescope. There is no single giant mirror pointing toward the sky. Instead, dozens of separate antennas stand across the high plateau of northern Chile, each receiving the same radio signal from a different location. Those signals are combined. The distances between the antennas allow the array to behave like one much larger instrument, giving astronomers the sharpness needed to resolve structures that a single dish would blur together. By moving the antennas farther apart or closer together, ALMA can change the scale of detail it is most sensitive to. For the Boomerang Nebula, that mattered. The molecular outflow is enormous. Some structures are broad and diffuse, others are concentrated around the dark central waist. An instrument studying only one spatial scale could miss part of the system, or blend several components into one confusing signal. ALMA could separate them. It observed carbon monoxide, one of the most useful traces of cool molecular gas. Carbon monoxide is not necessarily the most abundant molecule in the nebula, but its rotational transitions are strong, predictable, and accessible at millimeter and submillimeter wavelengths. Each transition occurs at a known rest frequency. That frequency is the starting point. If a parcel of gas is moving toward Earth, the line is shifted slightly upward in frequency. If it is moving away, the line shifts downward. The effect is the radio equivalent of the changing pitch of a siren as an ambulance approaches and then recedes. Astronomers call it the Doppler effect. But ALMA does more than report one average shift for the entire nebula. It divides the spectral line into many narrow frequency intervals. Each interval isolates gas moving within a particular range of velocities along our line of sight. The result is a sequence of channel maps. One channel may show the most strongly approaching material. Another reveals gas moving more slowly toward us. Near the center of the line, the map is dominated by material with little line-of-sight motion, perhaps because it is traveling mostly across the sky rather than directly toward or away from Earth. Then the sequence crosses into redshifted channels, where the receding side emerges. Viewed rapidly, the maps resemble slices through a moving structure. The nebula changes from channel to channel because each image contains a different part of the flow. This is where the apparent waveform begins turning into geometry. Suppose a spectrum contains two strong peaks. Without spatial information, those peaks might look like two mysterious modes of molecular behavior. In an expanding shell, however, one peak can come from the near side moving toward us, and the other from the far side moving away. The separation between the peaks records velocity. Their relative strengths record temperature, density, opacity, and geometry. Their position across the sky reveals structure. ALMA combined all three. For Raghvendra Sahai and the team analysing the ALMA observations, the decisive result was not simply a sharper version of Hubble's bow tie. The molecular map contradicted the visual boundary. Hubble had shown two bright lobes divided by a dark waist. Earlier single-dish millimeter observations had suggested a broader outflow, but they could not reconcile that extended gas with the narrow optical structure. ALMA finally separated the regions by position and velocity. The apparent disagreement broke open. In the inner nebula, carbon monoxide traced the same bipolar cavities that Hubble had revealed through scattered light. Dense molecular material formed walls around those cavities. Farther out, however, the gas did not stop at the edge of the blue lobes. It continued into a much broader, rapidly expanding molecular cloud. The telescope had not merely found more material, it had shown why the earlier images looked incompatible. A dense lane of millimeter-sized dust grains near the center blocked much of the starlight and allowed radiation to escape mainly in opposite polar directions. Visible light therefore illuminated a narrow hourglass inside a larger molecular outflow. The bow tie was not the boundary of the nebula. It was the portion selected by light. That realization gave the spectrum a new physical meaning. Peaks and asymmetries could now be placed on the approaching wall, the receding wall, the broad foreground cloud, or the warmer central region. A line that looked mysterious when averaged across the source could become ordinary once its components were returned to their locations. The map had turned disagreement into geometry. Around the central hourglass lay a much broader, patchier, high-velocity outflow. It extended beyond the bright lobes and contained the gas associated with the most extreme cooling. The famous boomerang shape occupied the center of a larger molecular event. This wider outflow was not a perfectly smooth sphere. It carried uneven brightness, gaps, and irregular structures. Some patchiness may represent real density differences, Some may reflect variations in excitation or optical depth. Some may emerge because different layers overlap along the line of sight. The map was more complete than the Hubble image. It was not simple. Near the middle of the nebula, ALMA also detected compact continuum emission from the dark waste. Continuum radiation is different from a narrow molecular line. Instead of appearing at one precise transition frequency, it spreads across a broader range. In this case, the continuum pointed toward dust. That dusty central structure blocks visible light and helps divide escaping radiation into opposing directions. It also marks the region where the history of the outflow becomes most complicated. Cold molecular gas surrounds it. Faster bipolar material moves away from it. Older, broader ejecta extend far beyond it. The waste acts like the physical hinge between different chapters of the star's mass loss. And because the central region is hidden, astronomers have to infer much of that history from motion. Velocity becomes a clock. If astronomers estimate how far a parcel of gas has travelled and measure how fast it is moving, they can calculate an approximate expansion age. The calculation is imperfect. Gas can accelerate or slow down. The true three-dimensional velocity may differ from the portion measured along our line of sight. The orientation of the nebula must be modelled. Still, the pattern gives a chronology. Material far from the centre generally began travelling earlier. The compact inner structures formed later. Different apparent ages imply that the boomerang was not produced by one brief, uniform breath from the star. Its outflow changed character. A broad mass loss event created the enormous cold envelope. Later activity shaped the narrow waist and bipolar cavities. Faster material interacted with slower material already outside. That interaction may have compressed the walls Hubble illuminated so clearly. Now consider what happens to a spectrum passing through this layered system. One line of sight may cross the near side of the broad cold outflow, one wall of the inner hourglass and warmer gas closer to the centre. The cold foreground layer can absorb, the denser wall can emit. The warmer interior can produce a stronger excitation signal. Every layer carries its own velocity. Add them together, and the resulting spectral profile may look irregular, split or asymmetric. The signal is complicated because the nebula is complicated. This is why spatially resolved spectroscopy matters. A single spectrum averages everything inside the telescope beam. A channel map asks where each part of that spectrum originates. If the blue side of a line appears on one side of the nebula and the red side appears on the other, expansion or rotation becomes visible. If both appear along the same line of sight, front and rear surfaces may overlap. If an absorption feature is strongest against a bright background source, radiative transfer is involved. If a line changes only where a shock or dense wall is located, local excitation may be responsible. The spectrum stops behaving like a mysterious sound. It becomes a physical diagram, and that diagram places strict demands on any future claim of an unexplained molecular vibration. A genuine anomaly could not be established merely because a line looked unusual. Astronomers would need to show where the feature appeared, how its frequency compared with known transitions, whether it followed the established velocity field, and whether ordinary absorption, emission, and overlapping components could reproduce it. ALMA gave them the baseline. It mapped the cold rotational behavior already known to exist. It showed the speeds. It showed the walls. It exposed the hidden outer cloud. Any Webb observation would have to fit within that existing structure, or demonstrate clearly why it did not. But before we can judge what Webb might add, one remaining confusion has to be removed completely. The carbon monoxide lines mapped by ALMA arise mainly from molecular rotation. The dramatic title speaks of molecular vibration. The nebula itself is expanding through space, and a real oscillation would require change measured over time. 4 kinds of motion. 4 different forms of evidence. Until those are separated, even a perfectly real signal can be given the wrong name. The first kind of motion belongs to the molecule itself. Carbon monoxide is made from one carbon atom bound to one oxygen atom. The pair can rotate, but not with just any amount of energy. Quantum physics restricts the molecule to specific rotational states. Think of those states as permitted steps rather than a smooth ramp. A molecule can occupy one step, absorb energy and move to another. It can later release energy and fall back down. The radiation involved has a precise frequency determined by the difference between the 2 states. These are the transitions ALMA is designed to observe. The familiar labels COJ equals 1 to 0, 2 to 1, 3 to 2 describe changes in rotational angular momentum. They do not mean the molecule is tumbling at one easily visualized speed like a tiny propeller. They identify quantum states and the transitions between them. This distinction is easy to lose because astronomers use the language of motion. The molecule rotates. The gas expands. The spectral line shifts. All 3 statements can be true, but each describes a different scale. Rotational transitions tell us about energy stored within the molecule's allowed quantum states. Their strength depends on how many molecules occupy each state, which in turn depends on temperature, density, collisions and the surrounding radiation field. In very cold gas, fewer molecules have enough energy to occupy higher rotational states. Lower energy transitions become especially important. That is one reason carbon monoxide can remain such a useful tracer inside cold molecular environments. But molecular vibration is different. Instead of the whole molecule changing its rotational state, the bond between its atoms stretches or bends. In a larger molecule, different groups of atoms can move in several distinct patterns. One bond may lengthen while another shortens. Several atoms may bend out of alignment. The entire molecular structure can flex through quantized vibrational modes. These transitions generally involve more energy than simple rotational changes. As a result, many of them appear at shorter wavelengths, often in the infrared rather than at the millimeter wavelengths ALMA uses for cold rotational lines. This is the scientific doorway through which James Webb could enter the story. Webb carries infrared instruments capable of separating light into spectra. If warmer molecular gas or dust inside the boomerang produces identifiable vibrational features, Webb could potentially map those signatures across the obscured inner regions and the illuminated cavity walls. But that possibility must remain in the correct tense. Could, not did. A genuine detection would require a documented observation, a wavelength, an identified feature, an instrument configuration and an analysis showing why known alternatives failed. Without those details, the phrase molecular vibration is only a scientific-sounding label attached to an incomplete claim. Now comes the third form of motion. The molecule may undergo a perfectly ordinary rotational or vibrational transition, while the entire parcel of gas carrying it moves through space. That motion shifts the observed frequency. If the gas approaches Earth, the wavelength is compressed and the line appears blue-shifted. If the gas recedes, the wavelength is stretched and the line appears red-shifted. The transition itself has not changed. The moving source has changed how the transition reaches us. Imagine 2 identical clocks sending out perfectly regular pulses. One clock remains still, the other moves rapidly away. The moving clock's pulses reach you at longer intervals, even though its mechanism may be operating normally. Astronomical spectral lines behave according to the same broad principle. This allows astronomers to turn frequency into velocity. In the Boomerang Nebula, that ability is essential because the near and far sides of the outflow move in opposite directions relative to Earth. The gas on one side contributes blue-shifted radiation. The gas on the other contributes red-shifted radiation. material travelling mostly across our line of sight remains closer to the molecule's expected rest frequency. Combine all those regions, and the spectral line becomes wide or divided. One object can produce several peaks. One molecule can appear at several observed frequencies. Nothing about that requires the molecule to possess several mysterious identities. It only requires the gas to occupy different places and move in different directions. The nebulous shape makes the situation even more complicated. An hourglass is not a thin shell viewed from one simple angle. Its walls curve, its cavities open outward. The broad surrounding outflow overlaps it. Cold foreground gas can sit in front of warmer regions. Dust changes which background radiation is available for molecules to absorb. A single line of sight may pass through several physical environments before reaching the telescope. Each environment contributes something. One layer emits. Another absorbs. One approaches. Another recedes. One is dense enough for collisions to populate higher molecular states. Another is too thin and cold for the same excitation. The final spectrum is a negotiation between all of them. That negotiation can look like a vibration if we stare only at the finished line and ignore the structure that created it. But there is still a fourth category, a real oscillation over time. Suppose astronomers claimed that a molecular feature was pulsing, shifting back and forth or strengthening and weakening periodically. That would be different from mapping separate velocities inside a static observation. To establish such a pattern, one observation would not be enough. The telescope would have to return. The same regions would need to be measured again under comparable conditions. The suspected feature would have to change in a repeatable way. Instrumental drift, calibration differences, pointing changes and background variation would all have to be excluded. A spatial pattern is not automatically a temporal pattern. Two bright ridges on opposite sides of a cavity do not show that something travelled between them. Several velocity components do not show that the gas oscillated from one speed to another. A broad line does not show periodic motion. Time variability requires time. This is where sensational language often outruns the evidence. A complicated spectrum is described as a vibration. A variation across position is described as a wave. An irregular line profile becomes a pulse. Each word creates an image of movement, but the data may contain no direct measurement of movement through time. For the Boomerang Nebula, the safer scientific question is not, why are the pillars vibrating? It is, what combination of molecular transitions, gas velocities, excitation conditions and overlapping structures produce the observed spectral pattern? That question is less dramatic on the surface. It is far more powerful underneath, because each possibility predicts something different. If the feature comes from a known rotational transition, its frequency should match laboratory measurements, and its spatial distribution should follow the cold molecular gas. If it comes from a vibrational transition, it should appear in an appropriate infrared wavelength range and may trace warmer or more strongly irradiated regions. If Doppler motion produces the apparent pattern, the feature should align with the velocity structure already mapped by ALMA. If foreground absorption is responsible, the signal should be strongest where cold gas sits in front of brighter background radiation. If a shock excites the molecules, the feature may trace compressed boundaries where faster material strikes older, slower gas. And if a true oscillation is involved, repeated observation should reveal a consistent change over time. These are testable differences. The mystery is not an empty space where anything can be imagined. It is a narrowing path through competing physical explanations. This is also why combining telescopes matters. Hubble shows the scattered light structures. ALMA shows the cold rotational gas and its velocity field. An infrared spectrograph could reveal warmer molecular and dust features hidden behind the visible obscuration. Each Each instrument measures a different interaction between matter and radiation. They do not simply take sharper versions of the same picture. And when their maps are placed together, something remarkable happens. The boomerang stops looking like a pair of blue pillars surrounding a single mysterious signal. It becomes a layered physical machine. A dark waste controls illumination. Hollow cavities channel light. Dense molecular walls expand around them. A wider ultra-cold envelope continues far beyond the visible lobes. Warmer regions emerge where radiation begins returning energy to gas that once cooled below the cosmic background. Different wavelengths reveal different pieces because different forms of matter respond differently to radiation. The apparent contradiction between the images is not a failure. It is the information. Hubble and ALMA did not merely reveal more detail. Together, they change the shape of the nebula itself. And once that larger structure comes into view, the famous blue bow tie begins to shrink. Not physically, in importance. The Hubble image remains beautiful and scientifically valuable, but it stops being the complete object. It becomes one illuminated layer inside something much larger, colder, and more complicated. In visible light, the object appears strongly bipolar. Two opposing lobes dominate the scene, separated by a dark central waist. The edges look sharp. The interior carries arcs, filaments, and bright walls. Everything encourages the eye to imagine a narrow structure carved cleanly into space. ALMA revealed a different geometry. Cold carbon monoxide extended far beyond those bright lobes. The outer material formed a broader, patchier, high-velocity outflow surrounding the central hourglass. The visible boomerang was not floating alone inside empty darkness. It was embedded inside a much larger molecular envelope. The darkness around the lobes had been hiding matter. That is the first model change. Hubble had mapped where starlight escaped and scattered toward Earth. ALMA mapped where cold molecules existed and how they moved. The two observatories were not disagreeing. They were answering different questions. Where is the light? Where is the gas? Those answers overlap, but they are not identical. The dense molecular walls seen by ALMA correspond closely with the bright cavities seen by Hubble. This connection matters because it confirms that the optical structure is not merely an illusion. Real material shapes the lobes. Dense gas and dust form boundaries around regions where radiation can travel more freely. But those boundaries are only part of the system. Beyond them lies the great outer flow, older and more extended, carrying the thermal memory of the violent expansion that made the boomerang famous. Imagine the structure in 3 dimensions. The narrow waist hides the star. Bipolar cavities open above and below it, and the older molecular envelope spreads far beyond the neat bow tie shape. From Earth, all of those layers overlap. A bright filament may sit in front of a colder outer region. A dense wall may curve toward us on one side and away from us on the other. The near and far surfaces of the hourglass can contribute different velocities to the same patch of sky. A broad outer cloud can absorb radiation originating inside the brighter central structure. The spectrum becomes complicated because the geometry is complicated. This gives us a much more realistic explanation for a supposed molecular vibration inside the walls. Suppose one narrow region appears brighter at one wavelength and weaker at another. That could mean the molecules there occupy different energy states. It could mean the gas is denser. It could mean warmer material lies behind a colder absorbing layer. It could mean the wall is tilted so that a longer column of gas falls along our line of sight. Or it could mean the feature belongs to a completely different layer that only appears to overlap the wall from Earth. Projection creates false neighbours. Two structures can look attached while being separated by enormous distances along the line of sight. One can sit in front of another. Their signals combine inside the telescope beam, creating a pattern that belongs to neither region alone. Even a sharp image remains a projection. Astronomers still need velocity. temperature, and radiative transfer models to reconstruct its hidden depth. And then the temperature map adds another complication. The Boomerang is famous for gas colder than the cosmic microwave background. That description is true, but it can create the image of one uniformly frozen cloud. The real object contains a thermal history. The most extreme cooling occurred where gas expanded rapidly enough to lose internal energy faster than surrounding radiation could replace it. But as the outflow continued traveling outward, the environment changed, density fell. Dust and radiation interacted differently with the gas. Some regions began receiving energy again. ALMA observations found carbon monoxide emission beyond parts of the deepest absorption zone. That matters. Gas colder than the microwave background can absorb the background at the relevant transition. Gas that becomes warmer or more strongly excited can begin to emit instead. The change from absorption to emission shows that the nebula is not simply becoming colder forever as it expands. Some material is reheating. One leading explanation involves dust grains. Ultraviolet radiation from the evolving central source can strike a grain and eject an electron. That electron moves through the surrounding gas and transfers energy through collisions. The process is known as photoelectric heating. Across a nebula, that small interaction can change the thermal state of molecular gas. So the Boomerang contains at least 3 connected thermal regions: an obscured central environment where the star and dust provide energy, an extraordinarily cold expanding component where rapid adiabatic cooling dominated, and outer or exposed regions where heating begins to matter again. Cold is not the final state. It is one stage in the journey. This is the second model change. The object is not a static refrigerator left behind by a dying star. It is a moving thermal system. Gas is launched, cools through expansion, interacts with radiation, changes excitation, and eventually begins warming or dispersing. A molecular line recorded in one region may therefore look completely different from the same molecular transition somewhere else. Inside the coldest foreground gas, the line may appear in absorption. Along a denser wall, collisions may populate different rotational levels. Near a heated region, emission may strengthen. Across a shock boundary, line widths may increase. Through the center, dust may block one wavelength while allowing another to escape. If someone compared those locations without accounting for the physical changes, the spectral variation could look mysterious. But variation is exactly what a layered evolving nebula should produce. The harder question is whether the variation exceeds what known geometry, temperature and motion can explain. It requires astronomers to align visible images, molecular channel maps, continuum emission, and any infrared spectra inside one physical model. A feature becomes genuinely anomalous only when it survives that comparison. And this is where Hubble and ALMA together become more powerful than either alone. Hubble identifies the illuminated cavities and the fine structures shaped by dust and scattered light. ALMA identifies the cold gas, the dense molecular boundaries, the hidden outer outflow and the velocity field. One gives the visible architecture. The other supplies mass and motion. Placed together, they show that the Boomerang is neither a simple bow tie nor a featureless cloud. It is a nested system created by several episodes of mass loss and shaped by a hidden central engine. The outer flow is older. The inner hourglass is younger. The central waste is denser. The polar cavities direct light. The molecular walls preserve velocity. The coldest gas records rapid expansion. The warmer regions reveal that the thermal story is already changing. This structure is too organized to dismiss as random. It is also too energetic to explain comfortably as the ordinary final wind of one isolated star. The midpoint renewal, therefore, does more than enlarge the nebula. It changes the mystery. At the beginning, the question seemed to be whether Webb had detected an unexplained vibration inside two pillar-like structures. Now the deeper question is what event created a layered outflow large enough to become colder than the cosmic background, dense enough to build cavity walls, asymmetric enough to control illumination, and energetic enough to launch several solar masses of material into space. The alleged vibration is no longer the only anomaly. The entire energy budget is somewhere behind the dark waste. The star appears to have received help. Not from an unknown force, from another star. That is the leading possibility. Not a distant star passing nearby, not an explosion arriving from somewhere else. A companion already bound to the system, orbiting close enough to become involved in the death of the primary. The evidence does not show us a clean image of two stars colliding. It shows us what was left behind. An outflow containing several times the mass of the Sun. Gas travelling outward at extraordinary speed. A dense central waste. A later bipolar structure carved through older material. And an energy budget that normal wind from one isolated aging star struggles to pay. Something released a great deal of energy in a short period. Orbital motion may have been the hidden reservoir. Begin with a red giant. Its core is compact, but its outer atmosphere has expanded enormously. The edge of the star is not a solid surface. It is a vast, diffuse envelope, only weakly held by gravity compared with the material closer to the core. Now place a smaller companion in orbit around it. At first, the companion may travel outside the giant's atmosphere, but as the primary expands, the envelope reaches farther outward. Eventually, the companion begins moving through gas. That changes the orbit. The companion no longer travels through empty space. It experiences drag. Each orbit transfers energy and angular momentum into the envelope. The surrounding gas is stirred, heated and pushed outward. The companion begins spiraling inward. This stage is called common envelope evolution because the compact core of the giant and the companion temporarily move inside one shared gaseous envelope. It is one of the most violent and least easily observed phases in close binary evolution. The entire event may unfold quickly by stellar standards. Astronomers often discover these systems only before the interaction becomes severe or after the envelope has already been expelled. The middle is difficult to catch. Yet that hidden middle can transform everything. As the companion falls inward, gravitational potential energy is released. The orbit becomes tighter. Energy that once belonged to the orbital motion is deposited into the surrounding gas. If enough energy is transferred, the envelope can be unbound. Material that had been part of the red giant is thrown into space. This offers a possible solution to the boomerang's first major problem. The ordinary radiation and pulsations of one aging star may not provide enough momentum or kinetic energy to drive the observed outflow. A decaying orbit, however, contains an additional reservoir. The companion does not need to explode. It only needs to fall. The closer it moves toward the central core, the more orbital energy can be released. That energy can accelerate enormous amounts of gas. But the model is not a free answer. Astronomers cannot simply say binary interaction whenever a nebula looks unusual. The proposed interaction has to reproduce the measurements. How much mass was expelled? How fast is it moving? How long ago was it launched? How much kinetic energy does the flow contain? How much orbital energy could the suspected companion have released? And did the event naturally create the dense waste and bipolar structure we now observe? These questions turn the binary idea into a testable physical model. The strongest binary argument did not begin with an imagined collision. It began with accounting. In the later ALMA analysis, Sahai and his collaborators used the measured extent of the ultra-cold outflow, its expansion velocity, its estimated age, its mass and its kinetic energy. Each quantity described a different part of the same event. The cloud was enormous. Its outer material had travelled for thousands of years. It was moving at roughly 164 kilometers per second, and too much of the original stellar envelope appeared to have been expelled for an ordinary red giant wind to remain convincing. Wouter Vlemmings described the boomerang as an unusually strong laboratory for testing the physics of binary systems containing a giant star. Larsok and Niemann emphasized the timing. Astronomers had caught the object during a short-lived period when its extreme cold could still be observed. Those roles matter. The binary model was not added because two stars make a more dramatic story. It was added because the measured outflow demanded an additional energy reservoir. An orbit contains such a reservoir. If a smaller companion entered the giant star's expanded envelope, drag would have reduced the orbit. As the companion spiraled inward, gravitational energy and angular momentum could have been transferred into the gas. Material that the giant could not eject through radiation and pulsation alone could then be accelerated out of the system. The measured aftermath points backward toward that hidden interaction. It does not photograph it. The distinction remains absolute. The observations establish the outflow's extreme properties. The common envelope scenario explains how two interacting stars might produce them. A final merger remains possible, but it lies one level higher in inference. The data show the bill. The binary interaction is the leading account of how it may have been paid. The common envelope picture also helps explain how material became concentrated into a denser equatorial region around the center. The sequence may have unfolded in stages. First, the companion entered the extended envelope and transferred orbital energy into it. Large amounts of matter were expelled, producing the broad outflow that later cooled so dramatically. As the interaction continued, material became concentrated into a denser equatorial region around the center. Then a later, faster bipolar flow moved outward through the paths of least resistance above and below that waist. The result was not one simple shell. It was the layered structure now reconstructed from the observations. Older material farther out. Younger, denser structure closer in. A wide and cold molecular flow surrounding a narrow, illuminated hourglass. The timing matters because it suggests that the shaping process changed as the interaction evolved. The broad outflow and the inner bipolar cavities do not appear to be identical parts of one perfectly steady event. The star system changed its behavior. That is exactly what an inspiraling companion could cause. At first, the interaction may have been relatively broad and chaotic. Later, as the orbit tightened and the central region became more structured, the outflow may have become more strongly directed. The dense waste acted as a barrier. Gas could escape more easily above and below it. Polar cavities formed. Faster material may have struck older, slower ejecta and compressed the walls. Hubble later revealed those walls through scattered light. ALMA revealed the molecular gas inside and around them. The two maps preserve the aftermath of the same hidden interaction. But there is another possibility inside the model. The companion may not have survived. As it spiraled inward, it could have approached the giant's central core. If the envelope was not expelled quickly enough, the companion may have continued losing orbital energy until the two objects merged. A merger would release additional energy and angular momentum. It could help explain why the boomerang's outflow is so extreme. Yet this is where the certainty must stop. No telescope watched the merger occur. No image shows the companion entering the envelope. The present central region remains heavily obscured, and the physical reconstruction depends on the mass, velocity, geometry, and age of the surrounding material. A merger is therefore not a direct observation. It is an inference. A strong one, perhaps, but still an inference. That distinction protects the story from becoming fiction. We can say that the observations demand an unusually energetic event. We can say that direct binary interaction is a leading explanation. We can say that a common envelope phase and possible merger can provide the missing energy. We cannot say that astronomers saw the companion disappear into the core. The data record consequences, not memories. And those consequences are already dramatic enough. Imagine the central system during the most violent phase. A giant star fills the inner region. A companion moves through its envelope. Each orbit becomes shorter. Gas is dragged into motion. Material thickens around the equatorial plane. The envelope begins leaving the system. Then the released gas expands. Its density collapses. Its temperature falls. The violent interaction creates the conditions for extraordinary cold. This is the deeper connection running through the entire Boomerang Nebula. The companion, if the model is correct, did not directly refrigerate the gas. It supplied the energy that expelled it rapidly enough to cool. Orbital energy became kinetic energy. Kinetic expansion produced thermal loss. The hidden violence at the center became cold at the edge. That chain links the suspected binary interaction to the carbon monoxide absorption detected thousands of astronomical units away. And it may also explain why the central waist is so important. The waist is more than a shadow across the visible image. It may be material left from the interaction itself, dense dust and gas concentrated around the orbital plane, preserving part of the system's final rearrangement. Inside that structure, ALMA detected compact continuum emission. The radiation suggests a dense population of dust grains, some much larger than the fine particles often imagined in a diffuse nebula. Those grains affect what we see. They block visible light. They redirect radiation toward the polar cavities. They emit at longer wavelengths. They may help heat surrounding gas when energetic photons release electrons from their surfaces. And they preserve chemical and physical information from the hidden center. The next layer of the mystery, therefore, does not lie in the distant ultra-cold cloud. It lies behind the dark waist, a region where the suspected companion may have transformed the star, where unusually large grains collected, and where every escaping photon is filtered before it reaches the bright walls outside. Behind that waist, the Boomerang Nebula becomes difficult to see precisely because so much of its story is concentrated there. Visible light struggles to pass through. The central star remains buried. The suspected remains of the binary interaction are hidden inside a region dense with gas and dust. Yet at millimeter wavelengths, that darkness begins to glow. ALMA detected compact continuum emission from the central waist. Unlike a narrow carbon monoxide line, continuum emission spreads across a broader range of frequencies. It does not identify one molecular transition. Instead, it often reveals warm or cool dust grains absorbing energy and re-radiating it at longer wavelengths. Those grains are not passive decoration. They control the appearance of the entire nebula. Dust near the center blocks direct starlight in the equatorial direction. Radiation escapes more easily above and below the waist, where the surrounding material is thinner or has been cleared by earlier outflows. That escaping light illuminates the polar cavities and the walls around them. The famous blue lobes begin here, not as two independent objects, as two directions in which light found a path. The waist therefore acts like a valve. It regulates where radiation can travel, which regions become visible and which parts remain hidden. But it also preserves evidence. Dust forms from material expelled by the star. Its composition, size and temperature depend on the conditions in which it condensed and on everything that happened afterward. Collisions can break grains apart. Dense environments can allow them to grow. Radiation can heat them. Gas can drag them outward. The grain population becomes a record of the central environment. In the Boomerang, the continuum measurements suggest that some grains in the waste may be unusually large, reaching millimetre or perhaps even centimetre scales, rather than remaining as tiny particles drifting independently through a diffuse cloud. That does not mean the centre contains smooth pebbles arranged in a visible ring. The inference comes from how efficiently the dust emits at different wavelengths. Small grains and large grains do not interact with radiation in exactly the same way. By comparing the strength of continuum emission across frequencies, astronomers can estimate how the grain population is distributed. Those estimates carry assumptions. The dust temperature matters. The total mass matters. The grain composition matters. The optical depth matters. A thick region can hide its own interior, making the apparent emission difficult to interpret. Even so, the central waste appears to contain a dense, evolved dust population unlike the thin haze visible in the outer lobes. This is important for the binary interaction model. A common envelope event or merger can drive material toward the equatorial plane. Gas with angular momentum resists falling directly inward. It collects around the centre, creating a disk, torus, or dense expanding waste. Inside that environment, particles can remain close enough to collide and grow. The same interaction that expelled the enormous cold outflow may therefore have left behind a more compact structure where dust continued evolving. The system separated itself into two physical worlds. Far outside, gas expanded rapidly and became extremely cold. Near the centre, matter remained dense, dusty and exposed to a changing radiation field. The outer flow records the violence of the ejection. The waste records what stayed behind. And between them lie the cavity walls, where radiation, dust and moving gas meet. That meeting point may be crucial to any real molecular anomaly. Molecules do not produce the same spectrum everywhere merely because they belong to the same species. Their energy states depend on their environment. A carbon monoxide molecule in the ultra-cold outer flow experiences conditions very different from a molecule near a warmer irradiated wall. Density changes collision rates. Temperature changes which energy levels become populated. Radiation can excite molecules without direct collisions. Dust can absorb one range of wavelengths and re-radiate energy in another. A shock can compress and heat a thin region, while the gas immediately beside it remains cold. The apparent pillars or cavity walls sit inside these changing conditions. One side may receive more direct radiation from the hidden star, another may be shielded by the waste. A curved surface may expose different layers to the observer. Cold material in front may absorb radiation emitted behind it. A spectral variation across the walls may therefore contain a map of the illumination geometry. This is where dust stops being merely something that blocks the view. Dust also heats gas. When an energetic ultraviolet photon strikes a grain, it can release an electron from the grain's surface. The electron enters the surrounding gas carrying kinetic energy. It collides with atoms and molecules, transferring some of that energy. Across a large cloud, countless interactions of this kind can raise the gas temperature. This process is called photoelectric heating. It offers one explanation for why parts of the Boomerang's outflow appear to be warming again after their extreme expansion-driven cooling. The gas did not fail to remain cold. Its environment changed. At first, expansion dominated. The material spread so quickly that its internal energy collapsed. Later, as density fell and different regions became exposed to radiation, heating mechanisms became increasingly important. The Boomerang therefore contains a thermal sequence. Material leaves the central system. It expands. It cools. It reaches an extraordinary minimum. Then parts of it begin receiving energy again. That sequence may occur across distance, but it can also occur unevenly across the walls and cavities. A sheltered region may remain cold, A directly illuminated region may warm. A shock may heat only a narrow layer. Dust density may vary from one arc to another. The resulting spectra could change sharply across what appears in an image to be one continuous structure. Again, no unknown vibration is required. Known physics can produce complex spatial patterns. But known physics does not mean simple physics. To model the signal correctly, astronomers would need to know the geometry of the waste, the direction of illumination, the amount of dust, the temperature of the grains, the density of the gas, the velocity field, and the molecular abundance. Each uncertainty affects the others. If the waste is more opaque than expected, less radiation reaches the walls. If the walls are denser, collisions become more important. If the gas lies in front of a bright infrared background, absorption may dominate. If it lies beside the background source, the same transition may appear in emission. A line can change without the molecule changing identity. The environment changes what the telescope receives. This is the physical trap hidden inside the title. A bright spectral feature across one wall might look like a new molecular mode. A weaker feature across the opposite wall might suggest asymmetry or oscillation, but the difference could arise because the central waste illuminates the two regions unequally. The signal might reveal the hidden architecture rather than unknown chemistry. That possibility is scientifically valuable. If infrared spectroscopy could map molecular or dust features across the waste in both cavities, astronomers could test how radiation escapes from the center. They could compare warmer inner material with the cold rotational gas already mapped by ALMA. They could look for shock traces along compressed boundaries. They could measure how dust properties change with position. And this is where James Webb becomes relevant for a real reason. Not because its name automatically transforms a claim into a discovery. Because its infrared instruments operate in a part of the spectrum where warm dust, molecular vibrational bands and obscured inner structures can become visible. ALMA follows the cold gas. Hubble follows scattered visible light. Webb could follow the energy being absorbed and re-emitted between them. But Webb would not simply take a sharper picture of the same boomerang. It would examine a different physical layer. The most useful Webb observation would not begin with a beautiful image. It would begin with a cube. 2 dimensions would preserve position across the Boomerang Nebula. The third would contain wavelength. Every small area of the dusty waste and cavity walls would carry its own infrared spectrum. That is what MIRI's medium-resolution spectrometer is built to produce. The instrument can examine mid-infrared radiation across a range where warm dust, molecular vibrational bands and several shock-sensitive features may appear. It would not see individual molecules. It would record the energy those molecules absorbed or released. Now imagine the observation. A narrow feature appears along the eastern cavity wall. It is absent from the western wall. It does not fill the entire dusty waste, and it does not follow the brightest visible filament. In the first reconstructed wavelength slice, it looks localized, sharp and difficult to identify. This is the moment when a sensational version of the story would stop. Webb found it. Scientists cannot explain it. The wall is vibrating. But the actual investigation would only be beginning. The observing team would first place the candidate wavelength against laboratory line lists. A known molecule may produce a vibrational transition there. A dust feature may peak nearby. 2 weaker lines may overlap closely enough to resemble one broad signal at the instrument's resolving power. If an identification looks plausible, the team would search for related transitions. A molecule rarely announces itself through one isolated mark. Its structure permits a family of transitions. Their strengths depend on temperature, density, collisions, and radiation, but they should form a physically consistent pattern. Suppose the companion features are missing. The candidate survives the first test. Now its position becomes important. The mirror cube is aligned with Hubble's scattered light image and ALMA's molecular velocity map. The eastern wall is not merely bright. ALMA shows that this section contains gas moving toward Earth. The western wall contains the receding counterpart. If the infrared feature belongs to material flowing with a cavity, its wavelength should shift consistently with that geometry. This provides a clean prediction. A related feature on the opposite wall should appear displaced in the other direction. The amount of displacement should agree with the known expansion within the limits of the infrared measurement. If it does, the signal is no longer an abstract vibration. It is tied to moving gas. If it does not, another explanation is needed. Perhaps the eastern wall is more strongly illuminated by the hidden central source. The dense waste may block radiation unevenly. A warmer patch of dust may excite the molecule only on one side. A local shock may produce chemistry absent from the opposite wall. The data cube allows each possibility to be mapped. One wavelength slice might trace warm dust in the waste. Another might outline both cavity walls. A narrow atomic line might concentrate near the hidden central region. A broad molecular feature might appear only where the fast inner flow meets older material. The ordinary image breaks apart into physical layers. This is what Webb could add to the boomerang. Not simply a sharper view of structures Hubble and ALMA already found, but a map of how infrared excitation changes from one environment to another. Hubble records visible photons scattered from dust. ALMA records transitions associated with cold molecular gas and separates that gas by velocity. MIRI could examine warmer material whose bonds and dust structures interact with infrared radiation. The observatories would be measuring different consequences of the same stellar death. Yet even a feature that survives molecular identification and matches a meaningful location has not earned the word unexplained. The team must ask whether the result depends on one portion of the data cube. Does it remain when the extraction region changes slightly? Does it appear in every exposure? Does it survive separate wavelength settings? Does it remain after the background is selected in a different defensible way? A strong feature should not exist only under one fragile processing choice. The observation would also need a reference field beyond the bright lobes. That requirement is difficult in the boomerang because the molecular outflow extends farther than the optical image suggests. A region that appears empty in visible light may still contain faint material from the nebula. Choose the wrong reference, and the pipeline may subtract real boomerang emission as though it were background. The hidden size of the object can therefore create a false spectral shape. This is not an abstract concern. It affects the central question. A broad dip created by oversubtraction could be described as molecular absorption. A residual background band could be mistaken for emission from a cavity wall. The source and the reduction cannot be separated casually. Then there is time. If the claim is merely that Webb detected a molecular vibrational transition, one observation may be enough to identify the feature. If the claim is that something inside the walls is oscillating, pulsing, or moving periodically, one observation is not enough. The telescope must return. The same location must be measured again. The feature must change in a repeatable manner that survives differences in pointing, calibration, and background. A static velocity gradient across the nebula cannot prove temporal oscillation. Neither can two bright structures on opposite sides of a cavity. A spatial pattern occupies different places. A vibration changes with time. That difference is the final boundary. Webb possesses the correct class of instrument to investigate warmer molecular and dusty structures inside the Boomerang Nebula. An integral field spectrum could connect infrared features with cavity geometry, shocks and the molecular velocities already known from ALMA. That's a strong scientific opportunity. But the discovery would not be defined by the telescope's name. It would be defined by a feature-surviving identification, geometry, velocity, calibration, and time. Until then, Webb remains the instrument that could perform the test. Not the proof that the title has already passed it. The first false anomaly does not move with the nebula. It stays fixed on the detector. Imagine several Webb exposures of the same cavity wall. Between observations, the telescope shifts its pointing by a small amount. The nebula lands on slightly different detector pixels, but a narrow bright mark remains at the same detector coordinate. In the first processed cube, the mark appeared to belong to the eastern wall. In the individual exposures, it belongs to the instrument. A bad pixel, unstable response or energetic particle event can survive long enough to resemble a spectral feature after the data are combined. The defense is movement. Real sky structure follows the sky when the pointing changes. Detector behavior follows the detector. This is why astronomers inspect the raw pieces before trusting the polished cube. The candidate feature must appear in independent exposures at the correct celestial position. It must survive bad pixel masks and alternative combinations. It must not emerge only after smoothing or aggressive noise removal. If it fails that test, the molecular mystery ends before molecular physics begins. The second false anomaly comes from apparently empty space. The boomerang's bright optical lobes occupy only part of its full outflow. ALMA showed that cold molecular material extends much farther. A background region chosen outside the blue bow tie may therefore still contain faint gas or dust belonging to the nebula. Suppose that region contains weak emission at the same wavelength as the candidate signal. The reduction pipeline treats it as background and subtracts it from every position in the science field. Now the cavity wall develops an artificial dip. The spectrum appears to contain absorption. Nothing absorbed the radiation. Real emission was removed twice. Reverse the mistake and a false bump can remain after insufficient subtraction. This is why background selection is not clerical work. It is part of the physical model. Astronomers must know how far the source extends and whether the reference field contains related material. A responsible analysis would compare several background choices. It would inspect fields in different directions. It would examine whether the candidate feature strengthens or weakens as the reference changes. A true localized line may vary slightly as the background is refined. It should not be created entirely by one convenient patch of supposedly blank sky. The third false anomaly is real radiation with the wrong identity. A spectrum from the boomerang contains contributions from different molecules, dust, temperatures and velocities. Two ordinary lines can lie close together. Gas moving toward Earth can shift one line toward another. Foreground absorption can cut through a broad emission feature. The final profile may look like one unfamiliar structure. Consider a broad peak with a narrow depression near its center. One explanation is a molecule with an unusual split transition. Another is simpler. Warm material emits a known line, while colder foreground gas absorbs at a related velocity. The two physical layers create one strange-looking profile. Change the extraction aperture and the shape changes. A small region centered on the warm wall contains mostly emission. A larger region includes more cold foreground gas, deepening the central dip. The anomaly is not a new molecular mode. It is radiative transfer across layered geometry. Known line blending creates another version. A weak molecular band and a dust feature may overlap at Miri's effective resolution. Neither alone matches the observed profile. Together they do. The correct test is not whether one known feature resembles part of the signal. Astronomers must construct a physically consistent spectrum containing every plausible contributor. Temperature matters. Density matters. Velocity matters. The expected companion transitions matter. If the same molecular identification explains several lines across the cube, confidence rises. If it explains only the most dramatic bump while failing everywhere else, the identification remains weak. These three failures, detector, background, and blend, remove many apparent discoveries. Then independent verification begins. A second reduction team should start from the raw exposures and make its own defensible choices. The team may select different background fields, extraction shapes, and artifact corrections. If both analyses recover the feature at the same wavelength and location, the result becomes harder to dismiss. The candidate should also survive cross-instrument comparison. If ALMA shows that the eastern wall approaches Earth, an infrared feature associated with that wall should behave consistently with the velocity field. If Hubble places the feature along an illuminated boundary, the excitation model must account for the radiation reaching it. Agreement between observatories does not automatically identify the carrier. It anchors the signal inside a real physical structure. Disagreement must be explained rather than hidden. Perhaps the infrared feature traces warmer material that ALMA's cold CO line does not. Perhaps it lies behind dust invisible to Hubble. Those are legitimate discoveries if the wavelength and spatial behavior support them. But if the feature follows detector coordinates, depends on one background choice, or dissolves into known blended lines, it is not an unexplained vibration. It is a solved data problem. Now suppose the candidate survives all three failures. It follows the sky. It remains under alternative background subtraction. Known lines and radiative transfer models cannot reproduce it. Independent reductions recover it. Its position connects with a physically meaningful part of the nebula. Only then does the word anomaly become useful. Even at that point, anomaly means that the current model is incomplete. It does not mean that quantum mechanics has failed. The next stage is to rank astrophysical explanations: unusual excitation, a shock, a rare molecular carrier, changing illumination, or genuine time variability. And time variability remains the hardest claim. If the feature is said to pulse or oscillate, Webb must observe it again. The same cycle must return. A one-time spatial gradient cannot become a vibration through language alone. The evidence has to move in time. Until it does, the signal may be unusual. It may be unidentified. It may deserve another observation. But it has not yet shown that the walls of the boomerang are vibrating. Something genuinely new belongs at the top of the ladder, not at the bottom. That order matters because an unusual spectrum does not arrive with its explanation attached. It arrives as a shape, a peak, a dip, a broad band, a split line, an asymmetry, or a feature that appears only in one region of the nebula. The shape is evidence. The interpretation comes later. So suppose the claimed signal survives the detector checks, background subtraction, independent reductions, and spatial comparisons. Suppose it genuinely belongs to the Boomerang Nebula. What could produce it? The first possibility is also the least dramatic. A known molecule. Space contains a large catalogue of molecular transitions. Some are strong and familiar, others are weak, blended or difficult to identify under unusual temperatures. A feature can appear mysterious simply because the expected carrier was not included in the first model. The same molecule may also exist in several isotopic forms. Carbon atoms do not all contain the same number of neutrons. Oxygen atoms do not either. Replace one common isotope with a rarer one, and the resulting molecule produces transitions at slightly different frequencies. These variants are called isotopologues. A weak isotopologue line can sit close to a stronger transition and distort its shape. Several ordinary lines can overlap until the telescope records one broad structure that resembles a single unusual band. The spectrum looks new. The ingredients are not. This is why astronomers search for companion transitions. If one feature belongs to a known molecule, other lines from that molecule should appear under the right conditions. Their exact strengths may vary with temperature and density, but the complete family must remain physically consistent. One unidentified bump is weak evidence. A connected pattern is stronger. The next level involves excitation. A molecule can exist throughout the nebula while producing a strong line only in selected regions. The difference comes from how its energy levels are populated. Inside the cold outer flow, collisions are infrequent and low-energy states dominate. Near the central waist, warmer dust and stronger radiation can populate higher states. Along an illuminated wall, infrared photons may excite molecular vibrations. Inside a compressed layer, collisions may temporarily increase. The molecule has not changed. Its environment has. This can make a familiar species appear to switch on and off across the apparent pillars. One section may emit, another may absorb, a third may remain invisible because too few molecules occupy the relevant state. Viewed as a map, the pattern could resemble a wave moving across the wall. But no movement through time has been demonstrated. The map may instead show an excitation boundary. Temperature differences create a similar effect. The boomerang contains gas that cooled below the cosmic microwave background, gas that is warmer than that minimum in regions where heating has begun to return energy to the outflow. A line sensitive to one temperature range may trace only part of that structure. Another line from the same molecule may favor a different region. If an observation combines them without resolving every component, the spectrum can become asymmetric or unexpectedly broad. That brings us to radiative transfer. Radiation does not simply leave every point in a nebula and travel cleanly toward Earth. It passes through foreground gas. It can be absorbed, scattered, and re-emitted. The amount that survives depends on optical depth, geometry, and the energy state populations of the molecules along the path. A warm region may produce strong emission. A colder layer in front of it may remove the center of that line. The final spectrum can develop two peaks with a dark valley between them. At first glance, those peaks may look like two separate motions or two distinct molecular states. In reality, one emission feature has been cut by foreground absorption. Reverse the geometry, and the line changes again. Place the cold material behind the warm source rather than in front of it, and the absorption may disappear from our view even though both regions still exist. Orientation becomes part of the spectrum. The hourglass geometry makes these effects especially important. The near cavity wall, far cavity wall, broad outer envelope and central source can overlap along one line of sight. Each layer contributes radiation or removes it. A complex signal may therefore be less like one voice and more like several conversations passing through the same wall. Then there is motion. ALMA has already shown that the boomerang contains material moving across a wide range of velocities. The approaching and receding portions of the outflow shift molecular lines in opposite directions. Several separate velocity components can create multiple peaks. A continuous velocity gradient can broaden a line. Turbulence or unresolved shocks can spread emission across additional frequencies. If an infrared feature follows the same velocity field, the apparent anomaly may be another tracer of the known expansion rather than an independent vibration. This prediction can be tested. The suspicious feature should be compared position by position with the molecular channel maps. If both respond to the same approaching and receding structures, the connection becomes difficult to ignore. The next level is a shock. The boomerang did not eject all its material at one speed. Faster later outflows may have encountered older, slower gas. Where they meet, the gas can compress, heat, and change chemically. Shocks are efficient molecular laboratories. They can break some molecules apart. They can free material from dust grains. They can trigger reactions that proceed slowly in undisturbed gas. They can populate higher energy states and broaden spectral lines. A feature concentrated along a cavity boundary may therefore trace a collision zone rather than a mysterious global oscillation. The visual test is direct. Does the signal follow the edge where fast material is expected to strike the older envelope? Does it appear with other indicators of heating or compression? Does its width increase where the interaction should be strongest? If so, the feature belongs to the dynamics of the outflow. Above shocks on the ladder lies genuine time variability. The hidden central source may not emit steadily. A surviving companion, a rotating dusty structure or changes near the stellar core could alter how radiation reaches the cavity walls. If illumination changes, molecular excitation may change with it. One wall could brighten while another weakens. A feature could vary without the molecular gas itself travelling back and forth. This would still be scientifically important. But it would be variable excitation, not necessarily a coherent physical vibration of the walls. Repeated observations would separate these possibilities. A changing illumination pattern should relate to the geometry of the waste and cavities. A propagating shock would move differently. A genuine periodic oscillation should return with a stable timescale and phase relationship. Time provides the distinction. Only after these explanations have been tested do we reach an unidentified molecular carrier. That phrase sounds dramatic, but it does not mean unknown physics. Astronomers have encountered spectral features whose exact carriers remained uncertain for years. The molecule may be familiar but difficult to reproduce in the laboratory. It may exist in an unusual charge state. It may be bound to a dust grain. Several related structures may contribute to one broad band. An unidentified carrier means the identification is incomplete. It does not mean nature has violated molecular theory. To climb one step higher, the feature would have to resist known molecules, isotopologues, dust bands, excitation gradients, radiative transfer, velocity structure, shocks, variability and instrumental effects. It would need to appear repeatedly. It would need independent confirmation. Its spatial behavior would need to contradict the established geometry, rather than merely complicate it. Its energy would need to fall where no plausible transition or combination belongs. Only then would researchers begin asking whether the physical model itself was missing something fundamental. And even there, caution remains. New chemistry comes before new forces. An incomplete molecular database comes before broken quantum mechanics. An unexpected local environment comes before exotic matter. The evidence must push the explanation upward. The headline cannot pull it there. This is the final value of the hypothesis ladder. It does not make the mystery smaller. It gives the mystery shape. At the bottom are explanations that require only known molecules in a complicated environment. In the middle are shocks, hidden geometry and changing illumination. Near the top are unidentified carriers and real time-dependent behavior. Beyond them, behind a gate that extraordinary evidence alone could open, lies genuinely new physics. The available evidence has not opened that gate. Not yet. What it has opened is a path toward a precise verdict. The evidence now divides into 4 levels. The first is what astronomers directly observed. Hubble recorded visible light scattered through dust in the Boomerang Nebula. Its images resolved the bipolar lobes, dark waste, arcs and filamentary structures that created the familiar blue bow tie appearance. ALMA observed carbon monoxide transitions and millimeter continuum emission. Its channel map separated molecular gas by velocity and showed that the bright optical lobes occupy only the inner portion of a broader, rapidly expanding outflow. The cold molecular gas is real. The absorption against the cosmic microwave background is real. The dense cavity walls, dusty central lane and large outer flow are real observational results. These measurements do not depend on a Webb attribution. The second level contains strongly supported physical interpretation. Rapid expansion explains how parts of the gas became colder than the microwave background. As the outflow spread into a larger volume, It performed work and lost internal energy. Dust near the centre explains why visible light escapes mainly in opposite polar directions. The apparent bow tie is therefore an illuminated structure inside a larger molecular cloud. Different temperatures, densities, velocities and lines of sight explain why one molecular transition can appear in emission in one region and absorption in another. The boomerang does not need unknown molecular physics to produce a difficult spectrum. Its known physics is already layered enough. The binary explanation also belongs at this second level, although with a different degree of directness. ALMA constrain the extent, age, mass, speed, and kinetic energy of the ultra-cold outflow. Those measurements are difficult to reconcile with a normal wind from one isolated red giant. An interacting companion provides an additional reservoir of gravitational energy. A common envelope phase could have expelled the stellar envelope, concentrated material around the equatorial plane, and helped create the later bipolar structure. The interaction is a leading physical reconstruction. A final merger remains possible rather than directly witnessed. The third level is what James Webb could test. MIRI could obtain spatially resolved mid-infrared spectra of the obscured central region and cavity walls. Such observations could reveal warm dust, molecular vibrational bands, shock-heated material and excitation differences hidden from visible light imaging. A Webb data cube could be compared with ALMA's velocity field, a feature that shifts consistently between approaching and receding walls would connect with the known outflow. A feature concentrated along a compressed boundary could identify a shock or a locally heated region. A signal that changes in repeated observations could support genuine time variability. These are real scientific possibilities. They are not evidence that the observations have already been made. The fourth level contains what remains unsupported. The source record used for this investigation does not establish a confirmed James Webb detection of an unexplained molecular vibration inside the Boomerang Nebula. It does not establish that physical pillars are oscillating. It does not establish a periodic molecular signal. It does not show that known molecules, Doppler motion, excitation, radiative transfer, shocks, background subtraction, and instrumental effects have all failed. And it provides no basis for new physics, artificial activity, or an unknown force. The exact verdict is therefore simple. The Boomerang Nebula contains extraordinary molecular motion and thermal structure. Hubble and ALMA have shown that directly. Webb possesses the capability to investigate warmer molecular and dusty layers that those observatories cannot measure in the same way. But the strongest claim in the title has not yet crossed the evidentiary boundary between possible observation and established discovery. That does not empty the story of mystery. It locates the mystery correctly. Astronomers still need to understand the detailed central interaction, the growth of the dusty waste, the thermal boundaries between ultra-cold and reheated gas, and the chemistry of the obscured inner structures. A future infrared spectrum could expose a new molecular carrier or a surprising excitation mechanism. It could reveal a shock hidden behind the optical lobes. It could even identify real variability if Webb returned and measured the same feature again. Those questions remain open because the evidence permits them to remain open. The unsupported claim is different. It is not an open scientific conclusion. It is a conclusion that has not yet been earned. So the title can now be answered without retreating into vague caution. Molecules in the Boomerang Nebula do rotate, absorb, emit, and move through a complex expanding flow. Their bonds may produce infrared vibrational transitions that Webb could investigate. But no verified result in the evidence base shows that James Webb has detected an unexplained coherent vibration within the nebula's pillar-like walls. The real discovery happened through a quieter chain. A dying stellar system expelled an immense molecular envelope. Expansion drove part of that envelope below the temperature of the cosmic background. Dust controlled which regions became visible. ALMA revealed that the famous bow tie was only the illuminated center of a much larger event, and the coldest gas left its most precise signature not as a brilliant flash, but as a small deficit in radiation arriving from behind it. That deficit belongs to the ending, because after every telescope, model and disputed label has been removed, one physical image remains. A cloud crossing ancient light. That is the Boomerang Nebula at its quietest and most revealing. Behind it, the microwave afterglow of the early universe fills the sky. The radiation has travelled for almost the entire history of the cosmos, stretched by expansion until it reaches us as a faint background at only a few degrees above absolute zero. The boomerang lies in front of a small part of that glow. Carbon monoxide molecules wait inside its expanding envelope. At most frequencies, the ancient radiation continues through. At a few exact frequencies, it does not. A photon carries the amount of energy needed to move a molecule between permitted states. The molecule absorbs it, far away. A radio telescope receives slightly less radiation than the cosmic background should have supplied. The missing energy becomes the measurement. It tells astronomers that the carbon monoxide is present. It reveals how its energy levels are populated. Combined with the spectral shape and a physical model of the outflow, it shows that part of the foreground gas became colder than the background behind it. Nothing needs to shine. The evidence is the darkness left in the spectrum. That is different from ordinary darkness. An empty region produces no signal because there is little there to interact with the radiation. The boomerang produces a deficit because matter is present and doing something precise. The cloud is not invisible through absence. It is visible because of it. This is the image worth carrying away from the entire investigation. Not a golden telescope hovering beside trembling pillars. Not an unidentified waveform detached from an instrument and wavelength. A molecular cloud crossing the afterglow of the Big Bang and removing a narrow portion of it. The gas became capable of doing this through violence. Thousands of years earlier in the version of the system now reaching Earth, a giant star lost most of its envelope. The material moved outward faster than an ordinary stellar wind should have managed. Its expansion consumed internal energy. The random thermal motion of the gas fell even while the outflow as a whole raced through space. Microscopic cold emerged from astronomical speed. The extreme state could not last. Radiation continued interacting with dust. Some outer regions began warming. The central remnant continued evolving behind the obscuring waste. The molecular envelope spread into a larger volume and became thinner. Larsok and Newman's observation about the timing carries particular weight here. Astronomers appear to be seeing the boomerang during a brief phase when such extreme cold remains detectable. The nebula is not a permanent cosmic freezer. It is a moment. The light reaching Earth preserves that moment after a journey of roughly 5,000 years. The central system we observe is already 5 millennia removed from whatever state it occupies now. Perhaps the hidden star is heated further. Perhaps more of the gas has begun to lose its molecular identity. Perhaps the ultra-cold absorption has weakened. Any radiation carrying those changes is still travelling between Centaurus and Earth. The boomerang therefore exists for us as delayed physical evidence. Hubble's blue lobes preserve starlight that escaped through the dusty waste long ago. ALMA's channel maps preserve molecular motion from the same distant past. The absorption line preserves a temperature state that may already have faded at the source. Astronomy cannot step outside that delay. It works within it. A telescope receives what has arrived, records how matter altered the radiation and reconstructs the event that produced those changes. That is why scientific language must remain tied to measurement. The universe offers no headline. It offers photons, missing photons, wavelengths, positions, and time. Humans build the explanation. Sometimes the explanation begins with more light. A star brightens, a spectral line appears, a shock glows. Here, the most memorable explanation begins with less. A narrow dip against a universal background. The dip is not dramatic to the eye. It would disappear inside a thumbnail, yet it contains more physical information than any invented vibration. It connects quantum energy levels to the death of a star. It connects a carbon monoxide molecule to the expansion of a cloud more than 100,000 times the Earth-Sun distance. It connects an interaction hidden behind dust to radiation released near the beginning of cosmic history. And it connects Earth to an event that occurred thousands of years before its evidence arrived. There is no need to make the boomerang stranger than this. Its real structure is already almost unreasonable to human intuition. A star loses an envelope. The envelope races outward. Expansion cools it below the surrounding universe. Dust creates a bright shape that hides most of the material. A telescope sensitive to longer wavelengths reveals the concealed cloud. And the coldest gas becomes measurable because the background behind it is fractionally brighter. The entire nebula may eventually disperse. Its molecular walls will thin. The central source will change. The bow tie will no longer appear as it does in the images we know. But the radiation already absorbed cannot be restored to the beam that crossed the cloud. That small interaction has become part of the history reaching us. One photon entered the outflow. A molecule accepted its energy. The universe behind the boomerang became slightly dimmer. And 5,000 light-years away, we learned to notice what was missing.